Dear classmates, welcome back to the last video of DFT chapter. In this video, we are going to discuss 4 issues and solutions for DFT. The first one is long test time, the second one is large test data volume, the third one is too much overhead, and number 4 is how can we test the DFT itself. Now let's start with the first issue. This is a review of a single StarCAD4 test operation. At the beginning, we load the scan chain by applying L cycles to shift in our test pattern number 1. And then we capture the response from the circuit, followed by the unload operation, where we shift out the response captured by the scan flip-flop of test pattern number 1. At the same time, we can also load the second pattern into the scan chain. Suppose that the length of scan chain is L. We will need L cycles to load the scan chain and another L cycle to unload the scan chain, plus 1 cycle to capture the test response. So overall speaking, how many test cycles do we need to apply a test? Suppose the length of scan chain is L and the number of test patterns is big N pattern. Totally, we would need this many cycles. From this picture, we can see that we need to load the test pattern 1 and followed by 2, 3, all the way to test pattern N. At the end, we would need to unload the last pattern. So totally, we would need N plus 1 scan shift, each of which has L cycles. And then we also need to capture the response. Totally, there are N pattern captures. So this is our number of test cycles. For a specific example, suppose that we want to apply 5,000 test patterns to a CUT of which we have 10,000 scan flip-flops. So what is the number of test cycles? Suppose all the flip-flops are in a single scan chain. So L is equal to 10,000. And number of test pattern is 5,000. So we plug in this equation, we will get 5,001 times 10,000 shift cycles. And we have 5,000 capture cycles. Totally, we have 50 million and 15,000 cycles. This is approximately 5 seconds on a 10 MHz tester. This is quite a long test time. If we want to sell 1 million chips, then we will need 1,400 hours to test them. This is a very long time and the test cost is very high. So how can we improve it? To shorten the test time, we can shorten the number of flip-flops in a scan chain. So how can we do it? We can simply partition the scan flip-flop into small n scan chains. If we do this multiple scan chain partition, then L is determined by the longest scan chain in our CUT. This is because ATE shift all the scan chain together. For example, continue from our previous case. Suppose we have 10,000 scan flip-flop in our design. If we don't do a partition, then we have only one scan chain. So L is equal to 10,000. However, if we partition it into 3 scan chains, this scan chain has 4,000 scan flip-flop, this one has 3,000, this one has 3,000. In this way, L is determined by the longest scan chain in our design, which is 4,000. By this simple partition, we can reduce the test time by 60%. This is a huge reduction in test costs. However, the penalty is that we need more I/O pins. In this case, we need 3 scan input pins and 3 scan output pins. So, in summary, multi-scan chain is a very simple solution to reduce our test time. Now it's time for you to work on a simple quiz. Suppose we want to apply 10,000 test patterns to a CUT of 6 million scan flip-flop, and we partition them into 3 scan chains. The first scan chain length is 1 million, the second one is 1 million, and the third one is 4 million. So how many test cycles do we need to test this CUT? You can apply this equation to do the calculation. Question number 2. What if we balance the scan chain length so that L1, L2, and L3 are all 2 million? Now please pause the video and work on this quiz. Okay, have you done it? For the first question, we have 10,000 plus 1 by 4 million plus 10,000, which is approximately 40 gigacycles. This is a long test time, but if we balance the scan chain length, that will be only 20 gigacycles. This is a 50% reduction in test time. So from this example, we can see that a balanced scan chain length is desirable to reduce our test time. Have you got it correctly? So now let's look at the second problem, large test data volume. If we want to apply a scan test on the tester, what is the amount of test data to be stored on the tester? The amount of scan input data is equal to the number of test patterns times the number of scan flip-flops, and the amount of scan output data is the same. The amount of primary input data is equal to the number of patterns times the number of primary input, and the amount of primary output data is equal to the number of test patterns times the number of primary output. Continue from the previous example. Suppose we want to apply 10,000 test patterns to a CUT of 6 million scan flip-flop, and suppose the number of primary input is 20 and the number of primary output is 50. So the amount of primary input data is equal to 200 megabits, and the amount of primary output is 500 megabits. They are okay for a tester. However, the amount of scan input data is 10,000 by 6 million. That would be 60 gigabits. And the amount of scan output data is the same. These are very large memory requirements. As we can see from this figure, the test data volume rises very quickly with increasing circuit size. For an ordinary ATE which has 500 pins, each of which has 64 megabit memory, the total ATE memory available on this tester is only 32 gigabit. If we need 60 gigabit of test data, it cannot be fit in ATE. So this is a big problem, especially for large design. So what can we do to reduce the test data volume? Can we reduce the test data volume by multiple scan chain? Now it's time for you to work on this quiz. Suppose we apply this 10,000 pattern to a CUT of 6 million scan flip-flop. Now we partition them into 3 scan chains, and each of which is 2 million scan flip-flop. So how many scan data do we need? Please pause the video and work on this quiz. Have you done it? This one is simple. We still need 60 gigabit of test data. There is no reduction at all. So multiple scan chain actually does not reduce test data volume. So what can we do? Please see the test compression chapter. Now let's look at the third issue, too much DFT overhead. When we talk about overhead, the third thing we think about is area overhead. On the left hand side, this figure shows a chip without DFT, and this rectangle represents non-scan DFT. After DFT insertion on our right hand side, the scan flip-flop is larger than non-scan flip-flop. Also, we need routing overhead. We also have extra pins for DFT. So those are overhead of DFT. Besides area overhead, we also have timing overhead. Because the scan flip-flop is lower than non-scan flip-flop. And we also have power overhead because we have more transistors in the scan design, so we have extra power. Overall speaking, DFT requires about 5% timing overhead and 10% power or area overhead. So how can we reduce the overhead? One possible solution is partial scan. In a full scan design, we make every flip-flop scannable. For example, in this figure, we have 3 flip-flops and we stitch every one of them in the scan chain. The disadvantage of full scan is, of course, more area overhead than the partial scan design. But full scan has higher fault coverage and shorter ATPG runtime than partial scan. If we want to reduce the overhead, we can choose not to scan every flip-flop. For example, in this figure, the middle flip-flop is the original flip-flop, which is non-scannable. So we only scan the first and the third flip-flop. The advantage is that the area overhead and the timing overhead is smaller, but the fault coverage can be lower and the ATPG runtime can be longer. This conceptual picture shows the trade-off between area and the fault coverage. From the left to the right, we increase the portion of scannable flip-flop in the design. As we increase the scannable flip-flop, the area overhead would increase. On the other hand, the fault coverage also increase. So from this concept, we can see the trade-off between a non-scan design and the full scan design. And the partial scan design is somewhere in the middle. This table shows an example of a benchmark circuit S5378. This column shows the original design without scan. This column shows the partial scan, and the right hand side column shows the full scan design. The number of logic gates are the same, 2781. For a non-scan design, all of the 179 flip-flops are non-scan. For a full scan design, every flip-flop is scannable. And the partial scan, in this example, we have 30 scan flip-flop and the other flip-flops are non-scan. We can see that the area overhead increase from left to the right. In this example, the calculation of area overhead is the area difference between scan design and the non-scan design over the area of non-scan design. In this example, we assume one non-scan flip-flop is approximately the same area as 5 logic gates, and one scan flip-flop is approximately the same as 7 logic gates. And the number of faults are the same because we consider only the fault in the logic. And this row shows the number of controllable input, including primary input and the pseudo primary input. On the right hand side, it's the observable output, which is primary output plus pseudo primary output. We can see that this number increase from left to right, and the fault coverage increased from 70 to 99%. And the ATPG CPU runtime decreases significantly as we go to the right. And this row shows the number of test patterns, and this row shows the number of test cycles. For a non-scan design, we use sequential ATPG. So the number of test patterns is equal to the number of test cycles. For scannable design, we use combinational ATPG. So the number of cycles can be calculated by the equation that we introduced earlier in this lecture. Now it's time for you to work on a quiz. Suppose we want to increase the percentage of scan in our partial scan design. We want to make 100 flip-flop scannable. Now please calculate the area overhead of this partial scan. Again, assume that one non-scan flip-flop is equal to 5 logic gates and the one scan flip-flop is equal to 7 logic gates. Now please pause the video and calculate this number. Okay, are you done yet? For the original design without scan, we have 2781 logic gates plus 179 non-scan flip-flop. So the total number is 3676. For the partial scan design, we have 2781 logic gate plus 79 non-scan flip-flop and 100 scan flip-flop. So the total number is 3876. The overhead is therefore 5.16%. Have you got it correctly? If you remember, we asked a question in chapter 1 whether DFT is worth doing or not. We show this number comparing a design without DFT and with DFT. The total number of dies is smaller with DFT because of the area overhead, and the yield is lower with DFT because the die size is larger. But the fault coverage with DFT is significantly higher and the defect level is significantly lower. So the repair cost is much better with DFT. The conclusion was that despite the overhead, DFT is still very much worth doing. Now we can discuss the last issue, how to test the scan chain itself. Remember that in ATPG chapter, we talk about test generation for logic gates, but we did not consider scan chain in ATPG. So we assume that the scan chain is fault free. But this is not true. Actually, scan chain themselves can be faulty. So they must be tested too. So how can we test scan chains? We can apply the scan chain integrity test. In this test, a sequence of 0011, 0011 is shifted in and immediately shifted out without capture clock, like what is shown in this figure. The expected shift out value should be the same as the shift in value. When we apply this test, every scan cell in the scan chain undergo 4 different transitions: 0 to 1, 0 to 0, 1 to 1, and 1 to 0. In this way, we can detect all the stopgap faults and the transition faults in the scan chain. So the number of test cycles will be increased by 2L. So 1L is for shift in and the 1L is for shift out. So the second question would be, how can we test the LSSD scan chain? We can apply a flush test to test the LSSD scan chain. In a flush test, we hold clock C to 0 and clock A is 1, clock B is 1. In this way, the level 1 latch is in transparent mode and level 2 latch is also transparent. So we form a combinational path from scan input to scan output, like this. So when we apply a signal transition from 0 to 1 at the scan input pin, we can propagate this transition all the way to the scan output pin, and we can measure the delay time from SI to SO so that we can determine whether this scan chain is good or faulty. In summary, in this video, we show 4 issues of scan. The first one is long test time, which can be solved by multiple scan chains. And the number of test cycles is shown in this equation. And the second issue is the large test data volume. The detailed solution can be seen in the test compression chapter. And the third issue is too much overhead, which can be solved by partial scan. And the last issue is about testing the scan chain itself. The scan chain can be tested by 0011 sequence or flush test. In summary, despite of the above issues, scan is still the most popular DFT technique, and it is definitely worth doing. Finally, we have two FFT for you. Number one, we want to reduce the test time, so we have many scan chains. Can we share scan input-output pin to reduce the pin overhead? Number two, multiple scan chain does not reduce the test data. So what can we do to reduce the test data volume? These are two interesting questions that you can think about before watching the test compression chapter. Thank you for watching.